Hi everyone. So we're going to begin one of the most important chapters in the entire course, and this has to do with normal distributions, which is going to be the most used probability distribution that we will be using. So in the last chapter, we worked with discrete random variables, and particularly those where there were only a finite number of possibilities for x. And we were able to list all those probabilities. And we could actually give a geometric description of a probability distribution for a discrete random variable using like looks like a histogram, where we could just find the probabilities at x is 0, 1, 2, and so on, list them, and then draw a rectangle for each value of x, draw a rectangle so that the area of that rectangle was, or rather the height of that rectangle was equal to the probability that x was equal to that number. So, for example, this first rectangle we'll call it the 0th rectangle if we want. The height is the probability that x equals 0. Okay, so since the width is 1, the area is also going to be the probability that x is 0, and so on. Okay, and then this would be the area of this rectangle would be the probability that x is 1, and so on. So if we wanted to find, let's say, the probability that x is, let's say, that x is equal to 1, let's say, we'd just shade in this area right here. That would be the probability that x is 1. Or now let's suppose we wanted to find the probability that x was between 1 and 3. Well, if it was 1, 2, or 3, that would mean this probability plus this probability plus this probability. Okay, so this shaded area then would actually represent the probability that x is between 1 and 3. Okay. Now, what we have to try a different approach when we have a continuous random variable, because in that case there are infinitely many values of x, and we can't draw infinitely many bars. So what we can do is we do it a different way. We instead of drawing these areas, which are all rectangles, we consider areas under some kind of curve, and we let the areas under the curve represent probabilities. And then, the region that we want x to be in will correspond to a region will correspond to an interval on the x-axis, and then that will correspond to an area above the interval and below the curve, and that area will represent the probability. So if x is a continuous random variable, this probability distribution can be described by this curve, where the area under the curve has to be exactly 1, otherwise we can't use it. And the curve is always above the x-axis. And then if we took the area here between the vertical lines at x equals 2 and x equals 7, this area here, this would represent the probability that x is between 2 and 7. All right. And in general, with a continuous random variable, we want to talk about probabilities that x is in a certain range. We're not going to talk about the probability that x is exactly equal to a number, because you wouldn't if you just had a single number, you wouldn't have an interval here. Okay, and we have an area of almost basically 0. Okay, because the area of a line would just be basically 0. All right. So we're also going to we're not going to make a big deal whether we're including the endpoints or not. So this would be the same as the probability of x is strictly in between 2 and 7, or we could include 2 and exclude 7 or something. The probability is going to be the same. So we're not going to make a big deal if whether we include the endpoints or not. Okay, so a normal probability distribution. Okay, so if we say that a random variable has a normal probability distribution? Well, what that first means is that we're talking about a continuous random variable. And the graph that we're using is a very particular graph. Okay. We also know that first, the mean and the median and the mode of this random variable are the same. Okay, we've sort of talked about the mean, what the mean of a random variable is, the expected value. We haven't really talked about the median and the mode, but one thing you could think of is it's very similar to the idea of a median, and basically half the value. The median would be a middle value of all the possible values of x, and so on. The curve is symmetric and bell-shaped, just like the curve had to be when we were talking about the empirical rule. Curve is centered at the mean, and the area under the curve is 1, is exactly 1. And what we're going to have is the curve, the normal curve looks like this. Now, we're not really talking about just a single normal curve. We get a different, every distribution is going to have its own mean and its own standard deviation. So if we let mu be the mean and sigma be the standard deviation, we define this curve. This curve actually has an equation. It's given like this. And I do not want you to memorize that or write that down. I only write this down just to show you that this curve depends on the value of sigma and mu. Okay. What's more important is that you know the shape of this curve, because you're going to be drawing it a lot for the rest of the course. So it's centered at mu, okay, and then we have these 2 points here are the inflection points, what we call the inflection points, where the slope, the graph kind of starts bending up or down depending on your perspective. And this first inflection point would be exactly 1 standard deviation from the mean. So mu plus sigma and mu minus sigma. Okay. And so then we have mu plus 2 sigma, mu minus 2 sigma. And basically we're going to say that the unusual values of x would be past this number and less than this number. Okay. So this is the normal probability distribution. Now the good news is you do not have to enter this equation into your calculator, because your calculator already knows the formula for a normal distribution. You just have to give it the values of mu and sigma. Now of the many normal distributions we can have, we have a special name for something called the standard normal distribution. Its mean is 0 and the standard deviation is 1. All right, and before we had calculators that could do all this neat stuff, we had to use tables. And we will be using tables again, but that was, what we had to do is what statisticians had to do is they basically, you will see, we could transform any normal distribution to a standard normal distribution by doing a simple transformation. And then the values of the probabilities using this trap were listed in all these tables, and then they would have to look. The statistician would have to look up the values there, then do another transformation back to their own distribution. But the standard normal distribution is what this section is interested in. So. The main idea here is you want to use to find the area. The area under a curve corresponds to a probability. Okay. So in particular, let's say if we want to find the probability that x is between a and b, this is precisely the area that's between x equals a and x equals b and below the curve. So we have this shaded area here. And to find the actual area, your calculator will do that. It's actually as a result of some calculus, but again, this is a calculus-free course, so we won't worry about that. And instead what we do is we type in the following things into this command we have on our calculator called normal CDF. So the normal, it's called cumulative density function. In a way it's similar to the binomial PDF or CDF command. But here we have to give the endpoints A and B, and then we have to give the mean and the standard deviation, which in this case will just be 0 and 1. And in some calculators, you just give them the endpoints, and the calculator assumes you're talking about the standard normal distribution. If we want to talk about the probability that x is less than or equal to a, or strictly less than a, we're talking about this area right here. And even though this looks like an infinite area, this is actually going to be a finite, just because of the way the curve is defined. And since there's no real left endpoint, we say in negative infinity. But some calculators that will allow you to enter infinity or in negative infinity. If not, what you can do is you can replace it with a very large negative number, like negative 1,000. For a standard normal distribution, negative 1,000 or negative 10,000, that should work. Similarly, if we want to talk about the probability that x is greater than or equal to a number, or just greater than a number, we use this. In this case, our left endpoint is b, and then our right endpoint would be positive infinity. And you can replace that with like 10,000 or some big number like that. It won't matter. And then 0 is the mean, and 1 is a standard deviation. So that, again, this is for the standard normal distribution. So let me just do some examples here. So when you're doing the homework, you're going to, they might ask you, here is the curve, find the shaded region. Or they might ask you, find the probability that x is in this range. And really, you're just going to do the exact same problem. You're basically finding an area, which is the same thing as finding a probability. So let's say you wanted to find the probability that x is greater than or equal, or less than or equal to 1.18. We would use normal CDF of negative infinity, which we'll write. In this case, we'll just use negative 10,000. Should be enough. And then 1.1801. And it might actually help you when you're first doing this to draw a picture to see what's going on. So here's 0, and here's 1.18. And so we're talking about this region right here. Okay. And as you can see, it might be a very big region. So let's look at how do we do this? We turn our calculator on, and we want to, we're using a normal distribution, so we hit the distribution. And right there at the top, almost second from the top, is normal CDF. So we select that, and then we enter our values, which we said was, again, negative 10,000. Or negative infinity if you want, comma 1.18, comma 0, comma 1, and then close parentheses. Hit enter, and we see that it is 0.8809. We can round it to 2 decimal places, so that for 3 decimal places would be 0.881. Then, if we wanted to find the range of an x between negative 0.5 and 1.4, we would do, this would be normal CDF of negative 0.5, 1.401. Okay. If we enter that in our calculator, turns out to be 0.611. And this would, again, this would look like the area would look negative 0.5 is here, 1.4 would be over here, and we're talking about this area right here. So we are talking about 2 boundaries here. And then if we want to find the probability that x is greater than or equal to negative 1.67, this is a case where x is greater than or equal to that. Here's negative 1.67, and we're talking about this region right here. So this would be normal CDF of negative 1.67. Positive infinity, which we can take as just positive 10,000, and then 0, 1, and this turns out to be 0.953. Okay. All right. So thank you for this. Thank you for this wonderful command, normal CDF. It saves us a lot of time. Now, in the next video, we're going to see what happens when we're not using standard normal distribution, and we're going to find out that not a whole lot happens. Well, we just have to make a few modifications. So, thank you for your time. Go practice, and I'll see you next time.